Welcome students to the MOOCs course on advanced probability theory. This is lecture number 3. In the last lecture, we have discussed the basic notion of probability. In particular, if you remember, if x is a random experiment, with the set of possible outcomes being omega and S is a sigma field defined over omega, and P is a measure defined over S, then omega S P is a probability space. Okay. So, this we have discussed in the last class, and today we want to investigate properties of P when we know that if P is a probabilities measure, then P of omega is equal to 1, P of A is greater than equal to 0 for all A belonging to the corresponding sigma field S, and P of union over I A I, where each A I is a member of S, is equal to sigma over I P of A I, when A I's are mutually disjoint. This much we know. Now, let us investigate certain properties of P. 1. P is monotonous. What does it mean? It means that if A contained in B, then probability of A is less than equal to probability of B. It is very simple. So, let me give you a proof. Suppose this is my omega, and suppose this is my B, and suppose A is contained within B. So, suppose this is my A. So, observe that B is equal to A union B minus A. That means B minus A consists of elements which are in B but not in A. Therefore, these two are disjoint. That is very clear from the Venn diagram. Therefore, probability of B, since these are disjoint, we can write it as probability of A plus probability of B minus A. This is the set difference. Now, B minus A one can also write as A complement intersection B. You may find this notation in some other books, but basically these are same. Therefore, what we find that probability of B is equal to probability of A plus a quantity which is greater than or equal to 0. Therefore, probability of B is greater than or equal to probability of A. Now, we know probability of omega, the entire set of possible outputs, is equal to 1. Let A be contained in omega. Therefore, we can write omega is equal to A union A complement, complement with respect to omega. Therefore, P of omega is equal to P of A plus P of A complement. Therefore, 1 is equal to, since P of omega is equal to 1, P of A plus P of A complement. Therefore, probability of A complement is equal to 1 minus probability of A, where A contained in omega. So, this allows us to say probability of phi is equal to 0, since phi is equal to omega complement. Now, note, if a set is empty, we see that its probability is 0. Question is the converse true? If probability of A is 0, does it mean A is phi, that is empty set? That is the question. The answer is that no. Example, consider a student's grade. Suppose possible grades are A, B, C, D and F. Suppose this means fail. Now, suppose all the students have passed the exam. Then, if we pick a random student and obtain its probability of getting an F grade, since all students have passed, probability of F is equal to 0. Therefore, this set or the event F has probability 0, although it is not an empty set. Okay, students. So, I hope the distinction is clear. We are sure that if the set is empty, then its probability is going to be 0, but we cannot conclude that given a set has probability 0 or an event has probability 0, the probability of that event is going to be, then the event is going to be null. That is not correct. Now, in our last class, we have seen and we have recapitulated today that probability of A union B is equal to probability of A plus probability of B if A intersection B is equal to phi. Question: what if A intersection B is not equal to phi? Example: suppose this is my omega, this is my A and this is my B, and we are looking at probability of A union B. This is the probability that the entire portion is covered by the event A union B. What is going to be its probability? It is not equal to probability of A plus probability of B, since A and B are not disjoint. The result is probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. Proof: if we go back to the diagram, we can see that A union B can be decomposed into three parts. One is this. These are the elements which belong to A, but does not belong to B. These are the elements which belongs to B, but does not belong to A, and these are the elements which belong to both A and B. Thus, we can see that we can split the A union B event into union of three disjoint events, which we can write as follows: A union B is equal to A minus B plus B minus A plus A intersection B. Now, A is equal to A minus B union A intersection B. This is very clear. If this is my A and if this is my B, then we can say that A is equal to this union this. So, this is A minus B and this is A intersection B, and these are disjoint. Therefore, probability of A is equal to probability of A minus B, which is a set difference, you should not forget that, plus probability of A intersection B, since these are disjoint. Similarly, probability of B is equal to probability of B minus A plus probability of A intersection B. This region union this region. Therefore, from start we can write probability of A union B is equal to probability of A minus probability of A intersection B plus probability of B minus probability of A intersection B for this part and plus probability of A intersection B coming from here. So, after cancellations we get probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. Example: suppose we throw a die and observe the outcome. We know that there are 6 outcomes. That is omega is equal to 1, 2, 3, 4, 5 and 6. Let A be the event that the value is less than equal to 3. Therefore, probability of A is equal to, this event will be satisfied when the outcome is one of 1, 2 or 3. Therefore, probability of is going to be 3, total number of possible outcomes is 6, is equal to half. Let B be the event that the outcome is even. Therefore, we know the probability of B is, the event B occurs when the outputs are 2, 4 and 6. Therefore, probability of B is again 3 by 6 is equal to half. Therefore, what is the probability that the outcome is less than equal to 3 or an even number, that is A union B, that is probability of A union B is equal to now favorable outcomes for A union B are 1, 2, 3, 4 and 6. Therefore, probability of A union B is equal to 5 by 6. Now, what is A intersection B? The event A intersection B occurs if the outcome is only 2, because 2 is less than equal to 3 and 2 is an even number. Therefore, probability of A intersection B is equal to 1 by 6. Therefore, by our formula, probability of A union B should be probability of A plus probability of B minus probability of A intersection B is equal to half plus half minus 1 by 6 is equal to 3 plus 3 minus 1 is equal to 5 by 6. So, we verify the formula with respect to one example as well. For any two events A and B, probability of A union B is less than equal to probability of A plus probability of B. This is obvious. Why? Since probability of A union B is equal to P A plus P B minus P A intersection B. Therefore, this is a positive quantity which we are subtracting. Therefore, P A union B has to be less than equal to P A plus P B, and the equality will hold if and only if A intersection B has probability 0. Now, suppose the question is, what is the probability of A union B union C? So, as before, let me explain with a diagram. Suppose this is my omega, suppose this is one event A, this is another event B, and this is another event C. So, we are looking at the probability of the event A union B union C. That means, this entire thing should happen. What is the probability? Formula is probability of A union B union C is equal to probability of A plus probability of B plus probability of C minus probability of A intersection B minus probability of A intersection C minus probability of B intersection C plus probability of A intersection B intersection C. So, that is a formula. Let me prove it. Proof: probability of A union B union C, we can write it as union of two events, probability of A union B union C. Now, since it is union of two events, therefore, by earlier formula, this is equal to probability of A plus probability of B union C minus probability of A intersected with B union C. This is equal to probability of A plus, this we already know is probability of B plus probability of C minus probability of B intersection C minus probability of, now by distributivity of intersection over union, this we can write it as A intersection B union A intersection C. Now, note that it is also union of two events, therefore, we can apply the same formula. Therefore, probability of A union B union C is equal to, from here we get P A plus P B plus P C minus probability of B intersected with C minus probability of A intersection B plus probability of A intersection C minus probability of A intersection B intersection A intersection C, which is equal to probability of A plus probability of B plus probability of C minus probability of B intersection C minus probability of A intersection B minus probability of A intersection C and now this minus becomes plus. Also you note that A intersection B intersection A intersection C, since A is occurring twice, it is superfluous, we can take intersection only once. So, we write plus probability of A intersection B intersection C. So, that proves the formula. I give you a small thing to practice. Show by induction that if A1, A2, An are n events, then probability of union over ai is equal to 1 to n. That means, probability of A1 union A2 union An is equal to sigma probability of ai is equal to 1 to n. That means, I am summing up the individual probabilities minus sigma I less than j probability of ai intersection aj plus sigma I less than j less than k. So, here we are looking at all possible pairs of sets, here we are looking at all possible triplets of sets, and the last term is going to be minus 1 to the power n plus 1 probability of A1 intersection A2 intersection An. The proof is simple. Basically, the way we have introduced C and then used the distributivity of intersection over union, in a very similar approach, you will be able to prove this for n. Or in other words, you assume it for n and you show that it is true for n plus 1. Let me give you another property. Probability of A intersection B is greater than equal to 1 minus probability of A complement minus probability of B complement. This is very simple. Proof: we know probability of A union B is less than equal to probability of A plus probability of B. Replace A with A complement and B with B complement. Therefore, from star we can write probability of A complement union B complement is less than equal to probability of A complement plus probability of B complement. Therefore, 1 minus probability of A complement union B complement is greater than equal to 1 minus probability of A complement minus probability of B complement. So, you can see that we have already got the right hand side, we have got the inequality. Now, what is 1 minus be A complement union B complement? We know that A intersection B complement is equal to A complement union B complement. This is from our elementary knowledge of set theory. Therefore, 1 minus probability of A complement union B complement is equal to 1 minus probability of A intersection B complement, and we have seen that probability of A complement is equal to 1 minus probability of A. Therefore, this whole thing is going to be probability of A intersection B. Hence, this is probability of A intersection B, which is greater than equal to 1 minus probability of A complement minus probability of B complement. Okay. Let me now extend the result for n events, that is probability A1 intersection A2 intersection AN is greater than equal to 1 minus probability A1 complement minus probability A2 complement minus probability AN complement, or we can write it as probability intersection over I 1 to n AI is greater than equal to 1 minus sigma I is equal to 1 to n probability AI complement. How to prove it? We have seen probability of A intersection B is greater than equal to 1 minus probability of A minus probability of B. Therefore, probability of A1 intersection A2 is greater than equal to 1 minus probability of A1 complement minus probability of A2 complement. Therefore, the above result holds for n is equal to 2. Consider n is equal to 3. Therefore, we need to show probability of A1 intersection A2 intersection A3 is greater than equal to 1 minus probability A1 complement minus probability A2 complement minus probability A3 complement. So, probability A1 intersection A2 intersection A3 is equal to, we are now considering it to be intersection of two events. First event is A1, second event is A2 intersection A3. Therefore, we can write it as probability A1 intersected with A2 intersection A3. Since now there are two events, we can write for n is equal to 2, from there we can write this is greater than equal to 1 minus probability of A1 complement minus probability of A2 intersection A3 complement, which is equal to 1 minus probability of A1 complement minus 1 minus probability of A2 intersection A3, because sum of an event, probability of an event A plus probability of A complement is equal to 1, that we have already seen, is equal to, now this one cancels with this, we are left with probability A1 complement plus probability A2 intersection A3. Now, because of the hypothesis that the inequality is true for two events, therefore, we can write it as greater than equal to minus probability of A1 complement plus 1 minus probability of A2 complement minus probability of A3 complement, which is nothing but 1 minus sigma p of AI complement I is equal to 1 to 3. Therefore, we have proved it for n is equal to 3. Let us assume that it is true for n is equal to m, that is probability intersection of I is equal to 1 to m AI is greater than equal to 1 minus sigma I is equal to 1 to m probability of AI complement. We need to show for n is equal to m plus 1. So, probability A1 intersection A2 intersection A m plus 1 is equal to probability of A1 intersection A2 intersection AM intersection A m plus 1. Again, we have split it into intersection of two events. Therefore, this is greater than equal to 1 minus probability of A1 intersection A2 intersection AM complement minus probability of A m plus 1 complement, which is equal to 1 minus probability of A1 intersection A2 intersection AM minus probability of A m plus 1 complement, which is equal to probability of A1 intersection A2 intersection AM minus probability of A m plus 1 complement. By induction hypothesis, probability of A1 intersection A2 intersection AM is greater than equal to 1 minus sigma I is equal to 1 to m probability of AI complement. Therefore, this result when we plug in here, we get that probability of A1 intersection N2 intersection AM plus 1 is going to be greater than equal to one minus sigma probability of AI complement I is equal to 1 to m minus probability of A m plus 1 complement, which is nothing but 1 minus sigma I is equal to 1 to m plus 1 probability AI complement. So, that proves the result. Therefore, by induction hypothesis, this is true for all n for any positive integer. Let me now state another property, which is called Bonferroni's property or Bonferroni's inequality. Which states that given n events A1, A2, An, probability of union over IAI is less than equal to sigma probability of AI, I is equal to 1 to n, and secondly, probability union over AI is greater than equal to sigma probability of AI I is equal to 1 to n minus sigma I less than j probability of AI intersection, or in other words, we have already seen the formula for probability of union over AI. That is a pretty long formula if the value of n is pretty large, but these two inequalities suggest that the value of this probability will lie between these two quantities. From the lower side, this is the bound, and from the upper side, that is the bound. So, proof 1, probability of union over AI is less than equal to sigma probability of AI, I is equal to 1 to n. We know probability of A union B is less than equal to probability of A plus probability of B. Therefore, probability of A union B union C less than equal to probability of A plus probability of A union B plus probability of C. That is, we are writing this event as union of two events A union B and C. Since there are two events, we can apply this formula and thereby we get this, and then we extend it one step further. Because A union B probability is less than equal to probability of A plus probability of B, therefore, we get this inequality. Suppose true for I is equal to n, we need to show for I is equal to n plus 1. It is very simple. Probability of A1 union An union An plus 1 is equal to probability of A1 union AN union AN plus 1. Thus, we have divided it into union of two events. Therefore, this is less than equal to probability A1 union AN plus probability of AN plus 1, and by induction hypothesis this is less than equal to PA1 PA2 plus PAN. Therefore, whole thing is less than equal to probability of A1 plus probability of A2 plus probability of AN plus probability of AN plus 1. So, this is pretty straightforward. So, let me now second part, that is probability union over I is equal to 1 to m A I is greater than equal to sigma probability of A I is equal to 1 to m minus sigma probability of A I intersection A j I less than j. Say, let us write it like this. Consider m is equal to 2. Therefore, we have probability A1 union A2, which we know is equal to probability of A1 plus probability of A2 minus probability of A1 intersection A2. Thus, for m is equal to 2, there is the equality. This we have already seen, but it satisfies this equation or this inequation. Consider m is equal to 2, 3. The probability A1 union A2 union A3 we have already seen is equal to probability of A1 plus probability of A2 plus probability of A3 minus probability of A1 intersection A2 minus probability of A1 intersection A3 minus probability of A2 intersection A3 plus probability of A1 intersection A2 intersection A3. Now, this quantity is greater than equal to 0. Therefore, probability A1 union A2 union A3 is greater than equal to sigma probability of I is equal to 1 to 3, that is this part, minus sigma probability of AI intersection AJ 1 less than equal to I less than j less than equal to 3, because this part is greater than equal to 0. Therefore, inequality holds for m is equal to 3. Let us assume that it holds for m is equal to n, we need to show that it holds for m is equal to n plus 1. Therefore, by induction hypothesis we have probability union over I is equal to 1 to n a I is greater than equal to sigma probability of a I is equal to 1 to n minus sigma 1 less than equal to I less than equal to j less than equal to n p a I intersection a j. To show for m is equal to n plus 1. Now, probability union over I is equal to 1 to n plus 1 a I is equal to probability union over I is equal to 1 to n a I union a n plus 1. Therefore, this is now we have written as union of two events. Therefore, we can use our earlier result. Therefore, this is equal to probability union over I is equal to 1 to n a I plus probability a n plus 1 minus probability of union over I is equal to 1 to n a I intersected with a n plus 1, because this is one event, this is another event. Therefore, this equality comes. Now, let us consider what is probability union over a I. By induction hypothesis, this is greater than equal to sigma probability of a I is equal to 1 to n minus sigma 1 less than equal to I less than j less than equal to n p a I intersection a j. This we get from this line. Therefore, this inequality comes here plus probability a n plus 1 minus this term probability union over I is equal to 1 to n a I intersected with a n plus 1. Therefore, this we can combine with this and we can write probability union over I is equal to 1 to n plus 1 a I is greater than equal to sigma I is equal to 1 to n plus 1 probability of a I minus sigma 1 less than equal to I less than j less than equal to n probability a I intersection a j minus probability union over I is equal to 1 to n a I intersected with a n plus 1. So, let us focus on this part. Probability union over I is equal to 1 to n a I intersected with a n plus 1 is equal to probability of, because of the distributivity of intersection over union, we can write it as, let me expand it for your understanding. Now, this is now union over n events, and therefore, by the first result we can write that this is less than equal to sigma I is equal to 1 to n probability A I intersection A n plus 1, because these are union of n events. We have seen in the first result that this union has to be less than equal to the summation of probabilities of the individual event. Therefore, minus probability union over I is equal to 1 to n A I intersected with A n plus 1, that is this quantity, is because this is less than equal to this. When we have taken the negative sign, the inequality changes. This is less than greater than equal to minus probability A I intersected with A n plus 1. Now, therefore, this whole thing, if I now consider this and I plug it in here, we get that the inequality is still satisfied because this part is greater than equal to this. Therefore, finally, we get the result that probability union over I is equal to 1 to n plus 1 A I is greater than equal to sigma probability of A I is equal to 1 to n plus 1 minus sigma 1 less than equal to I less than j less than equal to n plus 1 probability A I intersection A j. Proved. Okay, friends, I stop here today. In the next class, I shall solve one or two interesting problems with probability, and then I shall go to conditional probability, which is a very practical and interesting aspect of the theory of probability. Okay, friends, thank you so much.